Okay, class, welcome back. So today we discuss the lab work for the lecture number 3. So in the lecture number 3, if you remember, we discussed the we discussed over there the impulse response, and we saw that how the impulse response is used to find out the behavior of a function. So in this case, we use it to find the behavior of the correlation, and then we saw also the median filter. So here, open it up. So I put it as a part 2 of the lab 3 because I divided it into two parts, because both these chapters, lecture 2 and lecture 3, both these chapters, they are related. So here it is, the part 2. First of all, as always, I say that you must import all the libraries in the as a first cell or as a first command. So I run it, so I press shift and enter. So it will take time. So remember, over here I have three libraries: cv2, numpy, and matplotlib. And then I have one more command. This is called magic command. So the percent sign and then matplotlib in line, it tells that this is not a Python command, it's a command related to the Jupyter. It tells the Jupyter that you should show the images inside the same page, not as a separate window. So the first thing we will do is that we will discuss the impulse and the impulse response. So remember, impulse is a type of signal. In the signal processing terms, it is a type of signal that is used to find out the behavior of some circuit or some system. In the case of computer vision or images, impulse will be a signal which is shown over here like this one. So this is the impulse. Okay, so it is whole, all of the values are 1 except only single value in the middle, that is all of the values are 0, only the middle value is 1. So this is an impulse. So when you pass this value, the result will be the result that shows how the system behaves. Okay, so what is our job? We want to see how the mask is changed with respect to the correlation. So in the classwork, if you see over there in the class, in the lectures, we had the mask that was shown as A, B, C, D, E, F, so and G, H, I. So there were values from A until I. We can't put over here A, B, C, so we put over here the numbers. But all these numbers are different. So to see what will be the result, what is the effect. So we use the numpy array command. So we pass it these values. So it will create a matrix, 3 by 3 matrix, 1 until 9. So these are the values that are same, they are representing same thing as A until I in the lectures. So this is my mask. Okay, so I put different numbers because I want to see what will be the result. Then I will create my impulse. So I use this command numpy.zeros. So I create a matrix of 7 by 7 size with all zeros. And then I change the middle value, 3, 3 value. Remember, the indexing starts with 0. So 0 row, 1 row, 2 row, and 3 row. Similarly, the columns, column 0, column 1, column 2, and column 3. So row and column 3. Okay. So the impulse is like this over here. And then what we do is that we do over here cv2 dot filter 2d, and filter 2d is equivalent to correlation. So it will perform the correlation between the impulse and the mask, and we see the result. Store the result and check it out. Now this is interesting thing. This is the thing that is shown in your lectures. The result will be, because it is correlation, the result will be the 180-degree flipped version of the mask. So you see the result is this. 1 starts at the lower right corner, 2, 3, and then going up you will have the top left corner is 9. So it is the same mask, but it is flipped. Clear? So look at it carefully. Try to understand these things. This concept is important to know. So you note over here that the correlation which is done by filter 2D command in CV2, it will flip the image by 180 degrees. This is the case when your mask is not symmetric, but normally most of the time in our lab work, in our CV2, the filters that we use, they are normally symmetric. So symmetric, in the case of symmetry, there is no difference, it will be same. Clear? So let me run these commands again so that we go next. So next thing that we do is, after this, is the various correlation operations we saw in the lab work. So first of all, I will try to see that if I have an image, so this is my original image, this is fall leaves image, I want to correlate this image with impulse signal. So impulse signal is this one. So if if my mask has only one at the middle, this is an impulse. So if I correlate the impulse with any image, what will be the result? That's what I discussed in the class. Because there is a 1 here, there is no value in the surroundings, so it will not change anything. It will be the same result. So you see over here the same result. So there is no change in the image when it is correlated with the impulse. Important exam question. Okay, no change, it's original image. But if I take another case, now instead of impulse, I put all of them as 0. So you see over here, all the values are 0. The one I have removed it. So when it is 0, so it means that 0 will be multiplied with the whole image. The result will be 0. So in that case, I will get this answer. So these are typical exam questions. I will give you different masks and I ask you what can be the answer. So answer will be like this. It's a blank window. Everything is black. So the all zeros mask, it will produce the whole image as a blank image or black image. Okay. Then comes some little bit of more experimentation with this thing. Let's suppose you consider another mask or a kernel where the one is on the right side. So this is interesting. We discussed in the lectures, if it is on the right side, the image will shift on the opposite left side. Okay, so one is on the right side, image will be shifting on the left side. There will be a blank, there will be a column of pixels, black pixels on the right side. Clear? But this is what I explained in the class also, that these one column of pixels, it is not observable, very very small. You can't observe it over here, but there is one column of pixels on the border. Clear? So this is it, and let's run it. So there is one column of pixels here on the right. Same is the rule. If the one is on the left side, then the image will shift on to the right, and there will be a one column of black pixels on the left side. If the one is on the top, then there will be a black row on the top, and the image will shift down. Clear? This was it about filtering. And then there is a sharpening. So sharpening, if you remember, it means that the image edges will become more clearer, more sharp, more visible. So sharpening is the concept that is opposite to blurring. Okay, so I will first load an image. So this is the command. Remember this command I explained in the last lab lecture very clearly. So first I load the image img2. I set the image size 12 by 12. You can set any size you want, and then I display the image as a grayscale image. Okay, so I load this image, which is about the white blood cells in the human blood. Okay, now for any reason, let's say the scientists, they want to see the edges of the edges in the images more clearly, they can use the sharpening. So the sharpening mask or filter, sharpening mask or kernel, it is a mask where all the values except the middle one are negative, little bit small values but negative, and the middle value is positive and very high as compared to the surrounding values. So the surrounding values are like over here minus 1 by 9, all of them, and the middle value is almost reaching 2. So we make this mask like this. So we first create a matrix where there are all the values are 0 except the middle one is 2, and then subtract 1 by 9 matrix of 1 by 9, 3 by 3 matrix of 1 by 9. So when we subtract it, it will make this thing. It is up to you. You can make this mask manually. You can enter minus 1, 0.11 and all the values. You can make it yourself. It's up to you. So when I make the mask like this is my kernel K4. I can apply it sim method. I will use the correlation. So I take the image and I apply it, and the edges will be more sharper now. For some images it will be more clear. For some other images maybe it's not so clear. But here maybe you can feel the difference. The edges will be sharper. Clear? Most of the times you can use some other image or human face. There you will see the difference more clearly. So this was sharpening. And the last topic then is the median filter. Median filter, if you remember, it does not use the mask. It's an important exam question. Median filter is not like averaging filter or Gaussian filter. It does not use a mask. It will use window. The concept of window is used, but inside the 3 by 3 window or 5 by 5 window, it will arrange the values according to increasing order, and then it will select the middle value. So always the high or lowest value, black dot noise or white dot noise, they will always be on the boundary, on the far edges, either on the top, right side or the left side. So let's say here you have an image. So this image over here is contains salt and pepper noise, lots of white and black dots. Okay. So when you apply on this image, you for median filtering, you don't have any mask. You don't use a mask. There is a built-in function in CV2. It's called median blur. So it will apply this median filtering technique on the image. So here you have two. Median blur is used for median filtering, and it has two input arguments for this function. So you will provide it the noisy image, and then you provide it a number. This number over here shows what will be the window size. So window size, when you write 5, it means the window size will be 5 by 5. You can use 3 by 3, or you can use any other value you want. Okay, so when you do this, then it will give you this result. And if you remember the other filtering, the result over here in the case of median blur, it is much more better. So for salt and pepper noise and for impulse noise, median blur works better as compared to other approaches. Because what's the reason? Because it does not introduce any new pixel value. It will select one of the pixels from the neighboring values and it will put it over there. So the white and black dots are gone. Clear? Same median blur, if you try it on the impulse noise, now it is more difficult. So in the case of impulse noise, you have only white dots. So in this case, when you want to remove white dots, the result is there, but now this time the result is not so clear. And the reason mainly for this is because the image itself has a lot of bright areas. Image is much whiter. Overall, the image is much white. And the white dots, you can't separate it clearly because the image itself also has much white area. So remember, one of the rules for noise removal was that the neighborhood the area where you want to remove the noise values are much different from the normal pixels. Whereas in this case, the normal pixels and the noise, they have very close values, not too much different. Here, for example, look in this area, the hat. You have white dot, but most of the other times, the white dots are not so easily separatable. Clear? So that's the reason the result is not so good in this case. So this is our chapter lab number 3. For the assignment, if you come over here, assignment. So this is the assignment number 4. So lab 3 has got two assignments. One was before for part 1. This is for part 2. You have only two tasks. So date is 17th August. Task 1 is you take this human original.bmp image in grayscale and you try to sharpen the image and display the result as a 12 by 12 size image. And the second task is you take the shape impulse image. So this is an image of a ship with impulse noise, and you try to remove the impulse noise using the median filter. Median filter you will use of size, window size 5 by 5. Display result should be this size. Clear? So these are your tasks. So I wish you good luck and see you in the next lecture with the new topic.